Good morning. I'm Agnese Salvati. I'm a research fellow at Brunel University, and I work on urban microclimate modeling and building energy modeling. And with this presentation, I'm going to highlight some specific microclimate modifications that take place at the microscale. So as we have seen in the previous presentation, the urban system affect the climate, and we have different modification at different scales. We have the heat island effect that is determined by the overall urban system. Then we can have intra-urban air temperature differences that are determined by the variability of density and heights of building and presence of vegetation. But finally, we have specific urban spaces and streets and squares that have their own microclimate with a more micro-scale variability of the urban variables. When we go into real-world urban spaces, we need to focus to some specific aspects of the urban fabric, and especially the urban geometry and the material. The urban geometry, such as the building block geometry or also the urban vegetation, affect both the radiation balance and wind circulation. On the other hand, the material properties affect the amount of solar radiation that is actually absorbed or reflected toward the sky. So the combination of these two variables determine the so-called energy balance of an urban space and the wind circulation, and thus affect the potential for natural ventilation of buildings in urban areas and the radiant environment that also has an impact on the comfort, indoor and outdoor comfort. In this field and at this scale of investigation, I'm working on an EPCRC project called Urban Albedo Computation in High Latitude Location, an experimental approach. The project is led by Kent University in collaboration with Brunel University and Loughborough University, and aims at developing an urban albedo calculator. What do we mean for urban albedo? Is the capacity of urban geometry and material surfaces to reflect the solar radiation back to the sky. This is important because it has been shown that in a city like London, in this climate, an increase of urban albedo could mitigate the overheating effect during summer and without any detrimental effect or huge detrimental effect during the winter time. So we would like to increase the urban albedo of some areas in London, and to do so we need to have some model tools to predict with more accuracy the urban albedo. This project is developed through experiments and modeling, but the big novelty is that to study the global effect of urban geometry and materials on the radiation balance, for the first time, let's say we are using a scale model of a real urban fabric, and this case model is a big one. It's a 1:10 scale model, which allows to test the real effect of materials in real urban form. This is very different from very simplified models like the picture on top. That is what has been done so far. Of course, the city is quite different, so we are going to see what happens in real urban fabrics in terms of radiation balance, so that we can investigate how the urban albedo affects the energy performance and the comfort of buildings. We are using some case studies in London, and one of these is, for example, the area of Stanley Terrace in the borough of Islington in London, for which we already had collected in previous projects some background climate data that we use to calibrate also microclimate models, and we are also going to carry on a new monitoring of the air temperature in the area that will be also useful to compare how the climate has changed. So with surveys of 3D scan and surveys of the materials that are actually present in that area, we are going to develop accurate models, both scale models and digital models, to carry on microclimate analysis. So this is a representation of the ENVIMAT macroclimate model of the area with a simplification of the vegetation and the different materials. And here we can see some of the outputs of this simulation. For example, the 3 different profiles of wind speed and direction show that for sure the wind speed is much decreased, very decreased at the street level compared to the layers of atmosphere above the roof level, and also that the direction of the wind speed is very modified by the building layout. So this means that the potential of natural ventilation of these buildings is very variable and different. On the other hand, also the surfaces, the temperature of the surfaces is very variable, with maximum temperatures that varies between 30 degrees and 60 degrees, depending again on the combination of solar access and material properties. So we need to study the 2 aspects together in order to see how they affect the surface temperatures. And we are going to do this also to, the next steps of the project will be to analyze more in detail how the variability of the surface temperature, the facade temperature, affects the indoor environment of buildings, and so how they could be improved to mitigate the overheating risk. So this tool, the Urban Albedo Calculator, is expected to benefit a range of users and actors of the planning and design process, like urban designer, architect, and engineers that can use it to test the impacts of their design on urban climate. On the other hand, building simulator and modelers could use it to have more accurate, a more accurate description of the urban context to perform their thermal simulation. At the level of local authorities and urban planning, it could be used to guide the urban development process in order to improve the microclimate of the area, of the urban areas. But finally, also for paint or building material manufacturers, it could be used to show the effectiveness of these products when they are used in real urban fabrics. So finally, I would like just to conclude with some considerations that probably have been already anticipated, but in order to have an effective inclusion of this knowledge that we are developing, that actually it's in part already established, but it's ongoing. I mean, the knowledge on how the buildings affect the climate and how the specific climates of urban areas have an impact on the indoors and the thermal performance of buildings. We probably need to develop some urban microclimate regulations, because we have some regulation, for example, for building energy efficiency, but we don't have any regulation for urban microclimate guidance. So at the different levels, from the planning with some local climate zones, maps that can help the planning process, to the urban design level that can be guided using some kind of standards, microclimate standards, similar to the one developed for Hong Kong, for example, up to the final steps of the planning application that could be associated with some microclimate studies. In this way, we could actually include this knowledge in the planning and design, hopefully design better urban areas and environments. Thank you very much.